All right, so I just wanted to share a quick email. Russell Massey, who sits where Jade normally sits, had a little baby. Oh, we didn't say if it was even a boy or a girl. A baby. Was it a girl? Yeah. So I just wanted to say congrats on the baby. So if you guys all want to say congrats, Russell, on your wife. I don't know your wife's name. She did all the hard work. It wasn't him. Okay. So anyway, hope you don't get too many sleepless nights before now and Wednesday. But your wife will have them, I'm sure, for sure. So Mrs. Massey, hope you're having a great time. All right. What questions do you have? Sure, we'll go with Christopher. So you had a question about.
So how can you tell the difference between a 2-sample t-test and then the 1-sample when you're comparing the two?
Yeah, so a 1-sample t-test, remember when you look at the null hypothesis here, you're looking at a specific value. So mu equals whatever, 13, 31, I don't care, whatever. It equals a specific value, okay? That's a 1-sample, either a z or a t. So you're comparing it versus a specific value. If it's a 2-sample, t, it's going to be mu1 equals mu2. You don't know what either of those are before you start, okay? So if we've got a specific value mentioned in the problem, then that's what we're comparing it against.
As opposed to being given 2 sets of data.
Right.
Okay.
Okay? So that's the difference between a 1-sample and a 2-sample. Yes?
Can you just explain the difference between like a chi-square test of independence and a goodness of fit? Is the only difference just that one's dependent and one's independent?
Okay, so he wants to be, so those of you, for Russell, because I know Russell's going to be watching this, what's the difference between a chi-square goodness of fit and a chi-square independence test? They're both categorical, so that's not a difference.
You use the same chi-square equation for both.
Use the same chi-squared equation for both. Your expected values are different, right? But really, you're talking more of in the scenario case where you're not actually looking at data, okay? So the chi-squared goodness of fit is going to say, we want to know if it matches this preconceived idea. So I know in the book they said, we want to know, in fact, this is funny, since Russell just had a baby. There was an example in the book I remember, and it said, we want to know if there's a difference in the number of babies born on a specific day of the week, okay? And so the null hypothesis would have been there's all the days are the same. There's no difference among the days, okay? So what they did was they said, okay, so if there's no difference among the days, I think there were 500 babies born. So you would say, well, 500 divided by 7 would be whatever number that is.
Let's do 700, make it easy.
Yeah, 700 babies. You'd say 100 babies born each day, okay? So you get 100 on Monday, 100 Tuesday, etc., all the way down. And so you've got a preconceived notion of how many babies are born on each day, okay? So the other example I did was we did the population study. People are in the Northeast, and the Midwest, and the South, and the West. And they had like 23% in the Northeast and 27% in the South, or whatever the numbers were. Okay, so you're comparing it versus a specific value. So you're comparing it versus a specific model.
Like an ideal model.
An ideal model, yeah.
Whereas the independence, you're comparing each one to each other.
Yeah, the independence, you can think, so typically an independence test is you're comparing, in fact, it's also called homogeneity of proportions. So, yeah, so maybe you would want to say, so here would be an example of an independence test. So in Provo, you've got 90% Republicans and 5% Democrats and 5% independents. And in Salt Lake, you've got 80% Democrats and 10% Republicans and 10% independents. So you'd want to say, is the mix between those two cities the same. Now clearly those aren't, because I just made up the numbers. But the idea is you've got at least 3. You can think of a chi-square independence test as the ANOVA for categorical data. You've got 3. Well, you can actually do it with 2, but typically you use a chi-square independence on 3 or more proportions.
Didn't we get an example also where like the university offered 2 degrees and it was only 2?
Say it again.
We did an example about a university offering like 2-degree programs.
Oh, we did do that one. That was only 2. Yeah, the university offering 2-degree programs. I did that with 2. Yeah. So you can do it with 2, and I did do it with 2, but typically it's 3 or more.
Yeah, that's a simple.
Now, I will say this. I think I've mentioned this before. If you only have 2 proportions, you can either do it as chi-square or you can do it as 2 proportion. You should get the exact same p-value, despite the fact that they're wildly different methods. But it will work.
But you can do a confidence interval for 1.
And you can do a confidence interval for 2 proportion, but you can't do it for the chi-square. Chris?
So I understand when like it gives you data for what you're expecting, but when you have to calculate it, like with the childbirth, why wouldn't it be an independence test where you're saying that it's independent of what day they're being born on?
That's a good question. I wonder if you could. You want to do that one really quick?
Sure.
Let's see if we can do that, because it might not matter. That's a good question.
Or like with the question on the quiz with like the running shoes, like why is it the preconceived notion that they're equal?
Yeah, let's do the baby thing. In fact, we'll use nice numbers 700. Okay, so let's see if we can do this as either the goodness of fit. Well, the problem. Well, so here's the deal. So we've got our day of the week, and we've got our data. Okay, so when you're looking at this, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, okay? And so we've got our data, 102, 99, I don't know, I'm just making these up. 95, 110, 80, 100. Yeah, well, we were making it up, whatever. Here we're going to do equals the 700 minus the sum of all these. So then it adds up to 700. 114. Okay. All right, so we add that up. Okay, now here we go. Functionally, they're the same, but let's see. So normally we would say, so with the chi-square, the goodness of fit, we're just going to say it's 100 every day, right? Because they're all the same. Okay.
How do you find that?
Now, if I did this as a an independence, so if I add this up here, well, yeah, I'm going to be doing the same thing. I'm going to take, you know, if I do the row total times the column total divided by the grand total, well, that's going to give me just the same thing again. Yeah, that's not going to work. Because the row total is going to be the same as what your observed is. It's not going to make any sense. So in independence, you're going to have at least 2 columns. Well, then you're essentially looking at a proportion test. So yeah, if you try to do this as an independence test, these are going to be exactly the same, and that's going to be a problem. You've got to calculate that some other way, and so that's why it's a goodness of fit. Okay, Caitlin.
So we've done examples for goodness of fit in the past where we had the mean of something that had been in the past, and they wanted to know if it was greater or less than or like compared to the mean in the past, and it was a goodness of fit test because they had a preconceived idea.
Right.
So if we did it on the last one that is like equal to or greater than or less than, wouldn't that be goodness of fit? Like we did on the quiz, if you have the mean from something in the past, because we've done good.
Okay, so remember goodness of fit only works on categorical data.
But if it's like, is it greater than or less than it was in the past? Because I wanted to know how it affected the revenue. That's categorical, right? Is the revenue less than 44?
Are you talking about a specific scenario?
Well, I'm using the quiz as an example, but we've done things like that for goodness of fit before. That's why I was confused.
Well, so the quiz today, it was categorical data, wasn't it? Yeah, it was categorical data. So it's a goodness of fit.
Goodness of fit is categorical.
Goodness of fit is categorical, but I guess I'm not understanding your question then.
Because, so is it categorical if they give you the mean or something and then,
No,
and then it says, well,
not going to give you a mean because you can't get a mean off categorical data. It's got to be a proportion.
But it says if you have like a mean of like, we've done one like that before where they have the mean in the past and then it's like, is it greater than or is it less
There
than?
was one scenario I think we did about gas prices. It's not categorical data, it's quantitative, so that's got to be an F test, ANOVA.
So if you have a mean and they want to know if it's
If they have a
Greater
mean,
than
it's
or
not
less than?
categorical, so it can't be
So it
goodness of
can't
fit, period. Can't be. So it's got to be ANOVA in that case, probably. Okay, any other questions? Oh, I guess I wasn't sharing that. For those of you at home, Russell, that was our little spreadsheet that we did that I forgot to share. So the goodness of fit, you'd have to do it that way because if you did it this way, you'd just get the same values over and over. Okay? All right, what other questions do you have?
Can we go over probability of a type 2 error?
Ooh, probability of a type 2 error. What a good question. Those are too hard for me to think up. I'm going to have, it's a good thing
Well, I
I'm
have like a written example that we did in class already. I just want to make sure you know how to do it.
Okay. So we'll write this on the board, I think. Okay, so tell me what to write.
So it was the school that had 500 students and they wanted to know if,
So if your N equals 500 students,
and they wanted to know if like half of them weren't ready for
half ready
like college.
for college math.
And it said, what if
So your null hypothesis was
P equals 0.5?
P equals 0.5. Your alternative hypothesis was?
P equals 0.48.
Oh, well, so it was less than 0.5, right?
Yeah.
Now, under the type 2, we're saying that P equals 0.48. Is that correct? Okay. All right, so now how would we set up this problem?
Draw a picture.
Draw a picture. Okay? So we're drawing a picture. What's the mean of my picture? 0.5. I said the mean, but you know what I meant. Okay? Now, it's what kind of a test? The left-tailed test. So I need to figure out what that value is, right? How do I find that?
Z equals P hat minus P.
Z equals P hat minus P over
The square root of PQ over N.
square root of PQ divided by N. Okay. And what's my alpha, I guess? I probably should ask that. 1.5. Okay. So based on that, we can figure out what, if I convert that to a standard normal, this becomes 0, and this becomes, I've got 5% here. Excuse me. How do we find that value? We know what it should be on a standard normal, right? What should it be? Or how do you find it? Find it from the table. Okay. So if I share my table, Okay, I got my critical values there. The left-tailed test, 0.05, and I get what value? Negative 1.645 right there. Okay, so this value here becomes negative 1.645. Okay, so now how do I plug that back in the table?
How did you find it on the computer? You did that on the computer.
How do I find it on the computer?
You just the numbers.
Yeah. Equals, not Z,
Well, this,
norm S inverse, right? I don't think there's a Z inverse, is there? Oh, there's a Z test. I've never used that before. I don't know what that is. Norm S inverse. Probability 0.05. Yep, there it is. Okay. All right. Now, okay, so I'm plugging this value in for Z here. So I've got negative 1.645 equals P reject minus 0.5 divided by 0.5 times 0.5 divided by 500 square rooted, right? Okay, so now I need to solve for P reject. I'm going to multiply this over here. I'm going to add plus 0.5. So that kills that, plus 0.5. Okay, so now let's open up a new sheet here.
Wouldn't it be 0.5 times 0.95? Isn't it Q the?
0.5 times 0.5.
It's not 0.05.
It's not 0.05, it's 0.5. Okay. All right, so P reject equals 0.5 minus 1.645 times the square root of 0.5 times 0.5 divided by 500. So that gives me a value of 0.463. So if I go back here, so this question mark is no longer a question mark, it becomes 0.463. Okay, so what's next?
We do it again, but
This is where you bring your colored pencils, right? Okay, so we're drawing a new curve, and what's the mean of my new curve? 0.48, right? Type 2 right there. Okay, so now I've got 0.48, okay? A new normal curve. Now what?
do the same formula again.
Find the area to the right of the 0.463.
Yes, I need to, so I can draw a dotted line out here from 0.463, and I want this area to the right.
That's your beta,
That's your type 2 error. This is your beta.
and the black is your alpha.
Okay? So let's just remind ourselves, what is a type 2 error? Type 2 error, the definition is
When you
you don't, oh, somebody said the A word. Don't reject
Except the average.
the null when, in this case, so we said it was less than when P was greater than or equal to 0.48 in this case.
So you don't predict null when your hypothesis is true. When you're
No, the hypothesis was not true. It was less than 0.5, but so 0.48 is less than 0.5, but it's not my rejection rate. It wasn't low enough to distinguish.
When P does not equal 0.48, is that what that says?
When P was greater than or equal to 0.48. Okay, so we're rejecting it if we get a value less than 0.463. Well, we didn't get a value less than 0.463. It was actually 0.48. But we're just taking this area to the right.
and it's always going to be like that.
It's all, so if we go this to the left, that's going to be to the right. If we go to the right, this is going to be the left.
Did you have a two-tailed?
You could have a two-tailed. And it would be in between. You'd have to find 2 rejection regions and then find the area in between them. Okay? All right, so we're using the same equation again, but we're plugging in new values. So what should those new values be?
0.63 minus 0.48.
Say it again.
0.463 minus
463 minus 0.48 divided by
square root
square root of
0.48 times
0.48
0.52
0.52 divided by
500.
Okay. Now we can plug that in and we will get, so Z equals 0.463, which is that number there, minus 0.48 equals the square root of 0.48 times 0.52 divided by 500. And I get that divided by that, which is negative 0.75. Okay, so essentially what I've done, okay, so here I'm going to redraw my green curve here. It's kind of hard, I've got too much crowding here. Okay, so essentially what I've done, I'm redrawing the green curve. Okay, we think this value is 0.48. We're going from 0.463, okay, 463. I've converted the 0.48 to a 0. I've converted the 4.63 to negative 0.75, 1, and I want this area to the right. What does Excel tell me? Area to the left. So do I need to subtract from 1?
Yes.
Yes, I do. 1 minus norm S dist of negative 0.751. That's essentially what I'm doing. Okay? All right, so
The area to the left or to the right?
I want the area to the right. But Excel is going to tell me the area to the left, so that's why I need to do the 1 minus. Okay? All right, so now, if I share again, that's why the pictures are critical. 1 minus norm S dist of that, and I get 0.773. So so 0.773, that's my probability of a type 2, given that P equals 0.48. Okay?
So that's just saying that you have a 77% chance of
Making a type 2 error. Yeah, which is a big chance to make an error, right? So what's the probability you don't make a type 2 error? 1 minus that, that's your power, right? So it's 1 minus 0.773, which is roughly 0.227. And that's not what you want to get. Okay? We want at least, hopefully 80% power. Okay? Make sense? That was a really good question, Shay.
Yeah.
I don't think anybody has asked me for a type 2 error on a final review before.
My notes are just messy, so.
Okay? Did you get it right?
Yeah.
Okay. All right. So just as a reminder, if you want to watch the other video that's already posted, one of the questions that they asked is, what is all the commands, the Excel commands that we're going to need to remember? And I gave a pretty good list. I hope it's all of them, so no guarantee.
Wednesday at 9.
Wednesday at 9 for you guys.
Opens on Monday.
Monday, Tuesday.
Yeah, Monday and Tuesday is the computer exam. The written exam for you guys is Wednesday.
Are we allowed to bring any notes or anything to the computer?
No, I'll give you the formula sheet. Okay? All right. See y'all Wednesday.